Okay, let's start. Welcome, good afternoon. Welcome to my talk about building event-driven microservices with the Kafka ecosystem. My name is Guido Schmutz. I'm working for Trivaris for quite a long time, 21 years. I, of course, did a lot of things in these 21 years, started with PL SQL on the Oracle database, did some service-oriented architecture work in Java on Spring, and in the last 5 years, I did mostly big data and fast data projects with Kafka, with Hadoop, with stream processing, and of course, then microservices is also not far away. So maybe quickly show your hands. Who was in the Kafka talk this morning? Okay, maybe 80, 70, 80%. Who knows about microservices? Everybody. Okay, that's good. So I will start with a short kind of history. Where do we come from? So that's quite far back, almost 20 years. And then I will go to the microservice world. I will tell you why maybe microservices with events is better than just doing it synchronously, and then we will come to the chapter of Kafka. I mean, that talk is mostly, or is almost, is only about architecture, and I will start on a vendor-neutral way to explain you why is it better, and then at the end I will delve into the Kafka world, because I think it's important always on an architectural level to think about architecture and not about products. And products, they can change. Architecture, they usually, or they should be, a bit more stable. So where do we come from? Way back, we did maybe fat client applications on top, or web applications, rich UI application on the bottom. And mostly, when we did this, when we implemented these systems, they were all synchronous request response. So we asked for something, we waited until we got a response back. HTTP works like that. Calling a database, doing a select on a database works like that. The shared database on the right is also quite important. At the beginning, we just had one database where we shared all the data, and by sharing data through one database, we don't have to care a lot about integration. Then we said, world changes. So we have more databases, we have more systems, we don't have them all under control. So we said, let's do services. So let's expose services, or let's expose existing traditional functionality by services. We just added SOAP, contract first, maybe web services. Contract first, of course, was the good approach to think about a contract first, and then expose the functionality. The way we did it mostly is we added technical layers. So we talked about maybe a data service, a business entity service, a business activity service. Maybe we had process services. So they were like layered. The organization was layered. Each layer had its own services, its own contracts, and they were all reusable on each level. Of course, we said process services should only call activity service, should only call entity service, but the responsibilities were on that service level, often also on that technical layer. Then we added ESBs, service virtualization layers, just to make it a bit more decoupled, but important. We still have this synchronous. This icon here means synchronous. I forgot to explain it before, but I guess you have seen it. So it was still mostly synchronous request response. The service virtualization layer just added that layer that from a consumer, you don't have to know exactly where the web service runs, so you can decouple it a bit. But still, if the service bus is not there, or the service virtualization layer, and the service I want to talk to, I have a problem. It doesn't work because it's synchronous. What are microservices? I mean, all of you know about microservices, so I will do it rather quick. More or less the same system I showed you before with this layering, technical layering with customer, order, product, and stock. In a microservice world, of course, you organize it differently. You organize it on responsibilities, you do separation of concerns, and so you will probably talk about a customer microservice, an order microservice, product microservice, and so on. And you have the applications. The application, they talk with the microservices now. In a way, the term microservices compared to SOA, it doesn't mean really that this service is is smaller, although the name microservice suggests that. But in a SOA world, often the services were very small because they only did a technical, maybe a layering, maybe an abstraction of an existing logic. Okay, if you count the logic behind also to the service, but then still, you don't talk about the whole responsibility of a customer. You just talked about storing the data for a customer in the SOA world. So microservices, tightly scoped behind a clear interface, so we still have the interface. Highly decoupled is the idea, and maybe it's SOA done right. That's not from me, I heard that from other people as well. But in a way, especially the abstraction, especially owning my own data, I think that was always also the goal, or the goal of SOA was also like that, but it was just not feasible or achievable because we had to kind of reuse logic which was already there. And also at that time, there was no concept of container, there was no NoSQL databases. The databases we had at that time were very heavyweight, so there was no way to just have one Oracle database for each SOAP service. Nowadays, it's different. So a microservice, of course, can own its own data, and I think it's very important to say own or manage its own data. It doesn't have to be its own infrastructure as well. You still can have one single database, or not one single, but you can share databases between microservices, in my point of view. It's just important that you have your own schema, if there is a concept of schemas, or in a Cassandra world, you have your own key space. Of course, if you have really your own infrastructure, then you're very decoupled. But from a decoupled point of view, I think it's even more important to think about what interfaces do I expose, and what kind of technology I use, or what kind of semantic, and also how do the microservices talk to each other. So I mean, it's clear that from a consumer point of view here, we have to do we have questions for the microservice. We want to know the customer from the customer's microservice. We want to know about the status of the order. So we might ask the order microservice, what is the status of my order? But of course, microservices, they also need data from each other. So the order microservice at some point maybe wants to know about the customer. He only knows about the customer ID. He needs details about the customer. So another question here is, does the order microservice have to ask the customer microservice, as shown here, in a synchronous way? Just give me the customer data whenever I need it, at the point where I need it. Of course, you can also add API gateways to it, and then it becomes almost like the service virtualization we saw with SOA, but it's still synchronous. So we still talk synchronous request response with an API gateway most of the time. The problem, of course, with synchronous request response at the end is it only works if your partner you want to talk to is there. If he's not there, you have a problem. And of course, if service 7 in this picture here is not there and service 4 wants to invoke it in a synchronous request response way, and service 4 got called by service 3 and service 3 from service 2, and service 1 also invoked service 2 in a synchronous way, then of course the problem you have very down on a very, very low level just ripples back to the original one. And it doesn't just mean service 7 crashed. It could also mean service 7 is just overloaded and you get timeouts. Or it could mean a change of interface. If service 7 just suddenly changes its interface without communicating it before and maybe doesn't have a clear versioning concept, then of course that is also an effect which ripples through. And this is just not as loosely coupled as it could be. Of course, HTTP itself, the protocol, is loosely coupled or has some loosely decoupling inside it, but it's not as loosely coupled as it maybe could be. And of course, that comes to event-driven. Event-driven is not new. I think event-driven is just new or it's just fancy nowadays because now we have infrastructure which really supports event-driven and passing an event in a reliable and scalable fashion. Of course, we always passed events inside an UI application. I'm not a UI specialist, but there you have tons of events, button-click events. But it was just inside one single machine. And then maybe we passed events also between applications on the same machine still. And often these events were not persisted. They were just in flight, in memory. But if you want to reliably talk about events or pass events, then of course you need an infrastructure which supports that. And we had infrastructures like JMS, but the problem there is just, I mean, with JMS you can maybe send 200 and 300 messages per second, and then your queue is kind of not full, but it can't handle more. And with Kafka, we definitely talk about much more loads we can pass through, or with the concept of an event hub to be, if we want to stay product neutral. So why not event-driven? And of course, event-driven is not the answer for everything. That's very important. Because sometimes you need an answer. If you want to know the customer from your customer service, then you have to ask the customer service. It's kind of a query, and you want to get back the customer. Or here, with the sample, you want to ask the order service for all orders which has been added today, maybe, and you get a list of orders back. So this is a query kind of interface. Here you don't probably want to think about events. It doesn't have to be decoupled, because if you cannot reach you want to have an answer, you want to have it immediately. So if you can't reach the service, there's no way there's no help with events. On a command level, you have to think about, because command level, maybe you don't need an answer. And of course, here you see an answer. I have a command, order a product, order an iPad. And here the semantic says, I want to know true or false. I want to know if it worked on the order microservice. And this is kind of a control way or an imperative way of implementing my applications or communicating between systems, between microservices. You could do the same thing with events. You could just raise an event. You can just publish an event, of course, to an infrastructure which handles these events, to an infrastructure which reliably stores the events, so it doesn't get lost. And of course, this infrastructure has to be around all the time. But then you're much loosely coupled, because now you don't talk directly to the order service, order an iPad, and I'm waiting for an answer. I'm just publishing an event, and I hope, or I suppose, that somebody will handle that event and does the work which is necessary. But it's outside of my control. So that's the whole idea of event-driven versus, at the end, request-driven. But as I said, there is always the possibility, or there's always the query interfaces which you can't, or which you probably won't do in an event-oriented fashion. So if we change the picture, then on the front end, to the API gateway, to the applications, we might still be synchronous. But in the back end, we're now asynchronous. We're now publishing events. So now the order microservices doesn't have to ask the customer microservice anymore for the current picture of the customer. The customer microservice will always publish a new event when a new customer is added or when a customer changes. And everybody who is interested in changes of customers, they can consume that information. You know, now you might think, and of course, yeah, that's true. Now, if you publish an event, or if the customer microservice publishes an event, then it's the picture of that customer at that given second. And you cannot just leave it there and consume it if you need to know about a certain customer. So the idea here is that the order microservice is constantly consuming these events, customer changes events, and stores his own representation of a customer, everything he needs on his side. Because what I said, the microservice he owns his own data, or he owns its data. So a microservice, an order microservice, can also store customer data, but maybe he only stores first name and last name. Maybe he stores it concatenated together, because that's how he needs the information, and everything else is not needed. But now he has it on his side, and he doesn't have to ask the customer microservice anymore, and now he works even if the customer microservice is down or has a maintenance cycle, so it's much more decoupled. That's the idea of event-driven. And of course, if you have an event store here on the right side, the yellow thing, then of course this event store has to be reliable. It should never fail, so it has to be a cluster, it has to be distributed. it needs some kind of replication. So this one is now much more important maybe than your traditional databases you had so far. I mean, they're still important, but the event store is maybe from a reliability perspective more important than your databases or than your microservices. It's kind of the central nervous system, as Kai mentioned it this morning. Now you could say, what about streaming sources? Now what about like modern IoT flows or social media streams or click streams? Can I handle them as well? And now the question is, of course, probably not in a synchronous way. You probably don't want to get a tweet and you want to handle that tweet in a synchronous way and call your microservice in a synchronous way. That won't work. The question here is more, it's not, is it a microservice? The question is more, what is the technology I'm using? I now move the event store from the right to the left or into the middle, because now the event store is also a very good way to, as a first kind of point of retrieving events. So all the streaming data I don't have stored yet. I first store into the event store. Of course, I need some kind of sensor logic which accepts data from Twitter or from a IoT device, and this logic will store it into the event store. And now these events, they are available. It's publish subscribe. So the sensor logic publishes it to the event store, and the event store is publish subscribe, so everybody can subscribe on it. So a microservice could be a subscriber if it scales, if it can handle the throughput, the number of events, then why not? But the question here is more, what kind of functionality do I need? Stream processing systems, they provide you different functionality which you don't have in a normal like Java or Scala-based implementation or programming system or programming language, like windowing over a stream, like moving average over a window of time, because you have a consistent flow of events coming in, and maybe if you want to do a moving average of a certain amount, and you want to do it over 3 minutes, then a streaming analytics system is much easier to implement that functionality. And I would say stream processing, you can treat it as a microservice as well, because microservice is just an idea. And microservice tells you you're free to choose the language you want to use for your microservice. So a stream processing system is just another language, another implementation choice for your microservice. So on a picture, I would even move these together, or I would say this is all microservices and just different implementations we can choose from. And what's important, every microservice can consume, and every microservice can also produce again into the event store. So especially in stream processing, you derive some information. You derive an information like a moving average over 3 minutes, and the result out of that calculation is again stored or published back into the event store, so somebody else can consume that event, can be a subscriber of that information, and maybe do something. Maybe doing something is calling a service, like over here, calling a traditional system, because you now have found that some an anomaly happened, so you want to inform something, or you want to invoke a certain business process, so something is happening. This is what then either stream processing or microservice at some point, based on an event, of course, can do as well. Now, not everything is new, usually, unfortunately. You don't have greenfield all the time. It's nice if you have, but if you don't, then what about integrating legacy applications in such a picture? Legacy applications, they often come with a database. They often come with a relational database. They might be a fat client or an rich client, a web application, doesn't matter in that picture here, because here what matters is the database. And if you have a relational database, you have the concept of CDC, or change data capture. It's very old, but it's quite fashionable again, because in the past, CDC, change data capture, has been used to just replicate from one database to another. Maybe from Oracle to SQL Server, or Oracle to DB2, and then you have two instances holding the same data. now product vendors, such as Oracle with Golden Gate, but also new vendors, even in the open source space, Debezium, they create new functionality, or they change their change data capture functionality so that it can also send the events into an event store. So the same event store we have seen so far here can now get data from a traditional system, and it's events, because change data capture just sits on the redo log or on the change log of each database that has that, and just gets all the insert, update, and delete commands you send on a table. And on a low level, that's an event. It's an insert event, an update event, delete event. Of course, it's very fine granular. If your custom review consists of a customer table or a person table, an address table, a contact table, you get events for all these single tables. But it's events. And you immediately know that the customer has been added in a very old system. You can't really integrate, or you can integrate it by just querying the database and getting a full export, but then you have to do it, I don't know, every 5 minutes. And now you get it in a much more real-time fashion, and you get it in an event-oriented fashion, and you can treat it as an event. Like an event you get from an IoT device, like an event you get from a microservice. So at the end, these are all events, and they can be consumed from a stream processing or from a microservice. And yeah, as I mentioned, at the end you can just say this is all microservices. It's up to you. So in the picture, we just add these traditional systems, and now here you can see it's just tables or databases. We don't care about the logic because we integrate on table level, and we just get a constant change data capture stream. Of course, the load is not so heavy usually because, I mean, on these kind of systems, maybe a change doesn't happen every day on a customer. So the stream of event is not the same as the stream of events you might get from sensors. But the interesting part is that now you get events on a central place, and you can mix and match events from IoT devices with events from traditional systems, which provide you maybe changes of status information, of master data information. Still on an architectural level, and then we go over to Kafka. I will maybe fasten a bit. You also have CQRS and event sourcing, and I'll just try to explain it here in my own kind of words, because I think these terms are probably well known, but in my point of view, not everybody understands the same behind it. And I try to get different sources and merge them together into one picture. Maybe I'm correct, maybe I'm wrong. You can tell me after the talk. Of course, I'm interested. And so what I got, and of course, you can also mix and match these two principles. But command query responsibility segregation is also quite old, or it's called CQRS in short. The idea here is you separate write from read, and by that you can also use different data stores for read and different data stores for write. So, for example, you get on the upper level, you get the writes. So from a UI application, you get all your writes as maybe commands, and you store them in a write data store. It could be a NoSQL database, which is optimized for these writes. Maybe there's a lot of writes you get, and nobody asks for the data, or not nobody, of course, then you wouldn't implement a system, but you don't get a lot of reads, you get a lot of writes. In a time series system where you get IoT data, again, temperature values, you store it in a time series database, but only if something happens, if a customer thinks there's something wrong, he reads the time series. So it's a complete different pattern. So now you store it in a write data store, and then you produce materialized views on the bottom by a projection service, and these materialized views, they're now optimized for read. You could use a different database. And then you have a query service which is used to query the data. Of course, you can say this is not maybe not transactional. This is eventually consistent because it takes a while until the projection service has done its work, until it's available on the read side. So you can write something and you cannot immediately read it back in that kind of scenarios. But that's, in that case, you would have a use case where it's not important. And of course, it doesn't mean it's an hour later. You can write that in a way that it's a few milliseconds up to maybe a few seconds until this is updated. Event sourcing, on the other hand, is just treating the data which arrives as events and store them in an event store. And an event store just stores the events in the same order as they arrive. And then if you want to know the current state of your application, you need a replayer, and the replayer queries the event store and derives the picture out of the event store. So you could say, I'm starting, or have started 4 years ago, and I have all the changes of a customer stored in the event store. And now the replayer, what he has to do, he has to start 4 years ago and read everything and just basically do insert, update, 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 and derive the picture of the customer. Now you probably say, this is not fast. Of course, this is not fast. And that's why event stores, they might have the concept of snapshots. So you can do a snapshot, and the snapshot just means after maybe, or 1 year ago, I took a snapshot, so I can use that as a starting point and then just do the work. You can, of course, also publish everything which has been added to the event store. You can publish it to other applications, similar to what I've shown you before. The combination of these two is event sourcing and CQRS means I have an event store, and I'm using the event store as a source for the projection. So now I'm creating materialized views, and of course, I'm creating these materialized views just to speed up. So I don't need a replayer anymore. The replayer is kind of the projection service, and I'm creating materialized views. And if the event store never forgets, I can also create new materialized views much, much later. And I'm just reading from the beginning, and then just kind of bootstrap my new materialized view from the beginning of the event source. I'm reading everything, all the events I'm interested in to store in the materialized view. And after a while, that is ready, and I can keep it consuming, because now I'm getting the updates which are happening right now. So bootstrapping and staying consistent is one single logic if you do it this way. And then you have a query service which queries it. So this is kind of the combination of the two. You can already see it here, but I would like to go drill down a little bit. If you now work with an event store and state is the materialized view, then you might want to store in the event store plus in state. And if you do it in one logic, if the logic has to handle both, then you have a problem that these new systems, they're not transactional. So there's no way to combine these two writes in one single transaction. So if you do it this way on the left side, what I wouldn't suggest, then you might have that the first write has been successful, but you can't do the second write, and now you have a problem, of course, and you cannot roll back. So what you do, or what you should do, is you just use the event store as an inside your microservice as well. So everything you know about the world or about changes, you store in the event store, and maybe inside your microservice, you're a consumer of what you have produced. Because now it's decoupled. The publisher only writes to the event store, and somebody else, or the writer of the state, consumes from the event store. He's just another consumer. Of course, you have many other consumers as well, outside your microservice, which can handle the same event as well. And by that, you don't have this double write problem. And at the end, this is just a picture of an event sourcing inside a microservice. Now you just have the boundary around it with an event store, event handlers, projection handlers with state and query logic. And now from a concept of microservice where I said every every microservice owns its own data, and other people say every microservice owns its own database. We could have the same discussion on event store level. Has every microservice its own event store? Or do we have one central event store available for all the microservices? And it's just a responsibility question, of course. If it belongs to the microservice is responsible for the event store. If it's central, then it's part of an infrastructure. And if we talk about the central nervous system, of course it has to be central, because somebody has to just run that event store and has to make sure that it's always available. I mean, central means that's the goal, to have only one single one. Of course, because of security, because of maybe you also go to the cloud, you end up having more than just one, but you definitely don't have one per microservice, or you don't have one per consumer-producer pair. Before we go to Kafka, just one more question. What about historical data analytics? So far, we just said we can consume events, we do something, and we produce events. But sometimes you also want to do historical data analytics, of course. Big data or BI or deep learning or machine learning, it's all based on historical data, or most of the time. So what about this? In such a picture, I'm just adding something now to the architecture we already had, or have, the big data cluster. And the big data cluster is just a consumer. There's only one line. He's a consumer of the event store. If everything goes through the event store, he can just consume. He doesn't have to consume everything, but he can consume everything, and then you have everything in the big data cluster as raw data, or as raw events, or as events, even the events which flow between microservices. And that can be interesting as well from an analytics perspective. You don't have to think about loading your data warehouse or big data cluster anymore in various fashions, because you also want to know about what the microservices did with another microservice. There's just one single way of doing it through the event store. Okay, so that leaves me maybe 15 minutes to do the Kafka. As I mentioned, for me it was important to talk about architecture first. And everything I showed you, or most of everything I showed you is supported by Kafka, of course, because Kafka is one way to implement an event store. Or I would now say it's an event hub. People today use the term event hub, but at the end it's just a term. But Kafka is not the only way of doing it. So you have other options as well, and what I talked so far would be valid as well, and I hope that was helpful. But now with Kafka, most of you have been in the talk this morning, so I can skip that more or less. Kafka is just a cluster with multiple brokers. It has publish, subscribe. I think what's important is that when you consume, and that's also a huge change compared to a traditional message broker, so like JMS, when you consume, then you as a consumer have to know the offset. And the offset is nothing else than the pointer into the log. So the consumer has to tell Kafka the last position until he read the last time. So it's kind of a pointer. So far I have read, and now give me the rest, or give me the next messages. So by that, you can have different consumers, different consumer rates. So in big data, consumer might only consume every 15 minutes and might consume 1 million of events, because these are the events which have been queued up in this 15 minutes. And you have another consumer, a real-time consumer or near real-time consumer, who wants to know always the latest information. So he consumes always from kind of this empty one. So he just waits for the next message to arrive. And Kafka can handle both. Kafka stores the data on files, but Kafka is clever enough that it doesn't read from a file. If you're a real-time consumer, he uses file buffer cache. Because the data which gets written to disk, of course, is still in the file buffer cache if you're a real-time consumer. If you come 15 minutes later as a batch consumer, of course, the file buffer cache doesn't hold everything anymore, and then Kafka has to go to disk and read the data. But you're a batch consumer, it doesn't matter in that case. That is interesting, and that concept also allows you to always go back as far as you have data. Kafka never deletes. automatically, or Kafka doesn't delete based on a consumer pattern. Kafka doesn't know who are the consumers. Kafka doesn't know who has consumed until which point. And it could know it, but it doesn't care about it. And if it doesn't, because it doesn't care about, Kafka can also not automatically delete when the information has been consumed by everybody. So Kafka has a concept of data retention based on size or time. And you can also say, I never delete, if you want. And if you never delete, you just get an event log or your event store, which you started 4 years ago, and you still have all the events in that log. And you can always go back to the point 4 years ago and start from offset 0 and reread everything again. I'll come back to that. Kafka is more than just a broker or more than just that storage. Kafka has, of course, consumers and producers. You can write them in most of the languages you probably want to use today, Go, Java, C#, and so on. There is also a concept of Kafka Connect, and the green is Kafka Connect. So whenever you come from outside into the Kafka world, or you go from Kafka to the outside world, in the Kafka ecosystem, it's Kafka Connect doing that. Of course, there are other options outside of Kafka which can support you here as well, such as Spring Data Flow or NiFi or stream sets. This is just the answer of Kafka. What's very important is the schema registry. In my point of view, the schema registry allows you to communicate between a producer and a consumer the data you pass around. And of course, the stream processing would also retrieve the schemas from the schema registry. And these are Avro schemas. And Avro is just, the idea is to have a schema which defines what is a valid event. So consumer and producer, they know what to expect. And it also allows you to be backward compatible, so you can have new versions of your schema, and a consumer doesn't have to change immediately. He can just still consume with an old schema, and as long as it's compatible, the producer already produces with the new one. And that's quite important in these systems, of course, especially if you talk about communicating over microservice boundaries through Kafka. The data retention I already mentioned, so it can be never time-based and size-based, and there's an extra one. I think Kai didn't talk about that this morning. It's called log compaction-based, and it's quite interesting. Log compaction-based is based on the key, and I think that also hasn't been mentioned today. A message you put into Kafka always is key value. So you have a key, and you have a value. The value is the message or the event. The key is optional. You can use the key to use log compaction-based retention or storage. What does it mean? In these systems, you have two different events or two different streams. One is an event stream, where we just get all these single events. Now here it's on, let's say, person level. So Peter Muster, he got added on October 2015, and then he got changed in May 2017, and then again in 2017. So we have one insert and two updates for person 11. Person 12 only had an insert, and this is the event view. But maybe you're only interested in the latest state, in the latest representation of your customer. So now reading through a whole history of events and just applying insert, update, update, update all the time to get to the latest view is, of course, takes a lot of time and a lot of resources. So you can tell Kafka to handle it as a state stream or as a changelog stream, meaning that Kafka only stores the last event based on the key. And you would use the customer ID, so 11, 12, 21, you would use as a key. And Kafka does that all the time behind the scenes. It's like a process behind, which is constantly happening. And now you have a compacted topic, and that topic is smaller. And of course, if you start from the beginning, you have to read less data. to get a complete picture of your customers. Of course, this only works if your change always contains all the data. If your change only contains the address change, then of course it would not work. So that's something, of course, you have to control. And you can either do it in the left or right way. You could say the producer has to. Compaction is a property on topic level, and maybe you want to have both. So maybe you want to have the event stream view, so somebody can also get a historical view of your events, and you also want to have the right side view. And now, if you need that, you have to have two topics in Kafka. One is the full view, and one is the compacted view. You can tell the producer to create this view, or you could say the producer is always sending you the full picture, just the events, so the producer doesn't have to care about it. And then you just have an internal consumer producer, which is consumed from the topic, from the full topic, and writes it to the compacted topic, or the topic which gets compacted. And now you have two topics, and the consumer, a consumer who needs that information, can choose from which one to consume. And a consumer can be change data capture, and such a compacted topic is interesting, for example, for customer information, or now in that case here, it's driver information. So we have bus data, position data from buses driving around, and of course, usually don't get the driver name with that information. The driver is stored in a metadata storage system. You can get it maybe in Postgres, you can get it through change data capture, and now you have a driver topic. And the driver topic will be compacted, because you're only interested in the last or in the current information. And you could use that, you could use that information, for example, to store it in Elasticsearch, because your responsibility in that microservice is just to provide a new, better way to search for drivers. And you need Elasticsearch because you want a full text search. And the interesting topic here is that you can also add such a microservice much later. You could come up with that idea today. And if you have a compacted topic with all your drivers, which sits there since 4 years, you can just implement your microservice, and you bootstrap your microservice from that compacted topic. You just start at offset 0. You read everything which is available for your driver, just the latest information. And when you're at the end, you're basically on the current change data stream. Your Elasticsearch is populated, and now you're only getting the changes. Now, if a driver changes immediately today, you would get an update, and you update that in Elasticsearch. So your initial load and changing up to date is the same. And that simplifies it quite a lot. Because if you have to get initial load from that system and then synchronize it with the updates you get in order to not lose any single update, it's not rocket science, but you should better test it before you run it, because things can go wrong. I mean, here things can go wrong as well, but if it's the same logic, then it's much easier to test it, of course. If we add stream processing to the picture, and now this is just the idea to show you what Kafka Streams can provide, and we learned this morning that there's also a KSQL abstraction on top of it, and the idea here is just to say this is just a choice for implementing a microservice, and I would just like to show you what is possible with Kafka Streams or with stream processing languages or frameworks. In a stream processing, you always have a stream, of course, otherwise stream processing doesn't make sense. So you have a stream of, let's say, bus position topics. So these are the buses driving around, constantly telling you about the geo-position, and you have a driver topic. And the driver topic is just, you get it from this Postgres SQL database, change data capture. So this is master data information, and this is the stream. And you want to bring that together in order to enrich your stream. Your stream bus position only contains the geo data and the driver ID, and you enrich it by a join. And this is basically what you have in the stream processing. You can join tables, state, and streams. And you create a new topic. So you create new information in another topic, which is now the enriched event containing of drivers and bus positions. You can also aggregate. That's what I meant with windowing. So you could say, I want to know, I don't know, bus position, engine metrics, and I want to do some aggregation time window over a certain time. You do the join as well between the topics first, and then you aggregate. And what Kafka Streams does quite well is he has the concept of local result stores, because an aggregation is always state. And state you don't want to lose, especially if your window is has a certain length. If your window is, I don't know, an hour, then you have an hour of state. If you lose that state, if it's only in memory and you lose it, then of course there's no way to rebuild it, or the only way to rebuild it would be to reread an hour of data. But if you're constantly getting new data in, you might want to have that state survive, and that's what Kafka does with local states in a RocksDB database, and all the changes to that RocksDB database are again written into Kafka as a change log. So if that process here dies and you restart it, then that RocksDB can be populated based on the change data stream. It's just another topic used for internal usage, and this is quite clever. Of course, I cannot go into details because of time. And now we're almost at the end. This is the second last slide. That result store, so this is now just, it's the same picture. We just add an API and an application. Such a result store is also queryable. Flink can do that as well, and other languages probably, or other stream processing frameworks will follow. What is the idea here? You have a result store, a view of over a window of time, of a stream, of a certain calculation, and you would like to show that on a dashboard. The dashboard should just constantly change and just reflect the latest information. And with an application, you can query that. So you don't have to store it in another database, in a Cassandra or Elasticsearch, in order to be able to get that information. You can directly query it out of memory. Of course, you only have the picture, the latest picture. It will constantly change. There's no history of it. But if your dashboard should only show the current information, then of course that's what you want, and it's much simpler to achieve. This also works in a distributed fashion over a cluster. So summary, I basically just end with the architecture slide, and the only difference here is that this here has been moved together. You have an event hub, you have different processing units kind of consuming events, producing events, whereas maybe the top one, the batch data system, only consumes and does something. Maybe in some cases you would also publish back to the event hub, more as a signal that he has done his work. But the real information just flows between stream processing, microservices, or you could also combine that together. And the idea to combine that into one block is just the whole containerization. Because with container, of course, you can do everything on one single infrastructure. You could even add the event hub also to that same infrastructure, because an event hub can also run on a containerized Kubernetes Mesos kind of platform. Okay, that was it. Now maybe you have 1 minute left for a question, but I'm also here if there's more questions, just come to the podium. Thank you.
I have a very simple question. Maybe it's a bit a dumb question, but are these topics, are they schema-less, or do they have a schema?
It's not a dumb question. It's a very important one. Nobody has mentioned it today. They don't have a schema, so it's kind of schema on read. So it's only a binary. It's a byte stream, and you as a producer define what you write to. So you can just write JSON to it. You can write binary information to it, and of course the consumer has to know what you have written to. And by using a schema such as Avro, this is outside, and what you basically use Avro schema just to serialize it in a way that consumer and producer can work through the schema together. But it's not stored with the message to schema. It's schema-less. Yeah. Another one.
Yeah, hi, thanks for this. One question is, Kafka always persisting the events prior to making them available to consumers, or is this kind of in parallel?
Yes, it's always persisted. You have a choice of telling you if you're interested, if he has done it or not as a producer. You can produce and just tell Kafka, I don't care. So if something fails in the storage, then, and these are edge cases, of course, but then you don't know it and you lose messages. You can say you can tell Kafka when producing, I want to wait for the kind of first replica or for the master, for the leader partition. And you can also tell on the producer level, I want to wait for all replicas. And of course, the more you wait, the longer it takes for you as a producer. So, but that's throughput versus guarantees. And you have that choice, but it's always stored. Yeah. Okay, so thank you. And if you have questions, I'm here. Thank you.